You are watching DHTV from California State University, Dominguez Hills.
Hi, I'm Dr. Pamela Kreiser, and welcome back to NCR 507, which is Research Design and Interpretation. Today we're going to continue to lay the foundation for research methods. And as we talk about this session, what we will basically cover are some key statistical components that we want to explore, some basic principles, and then we're also going to talk about experimental design. Now, when we start the conversation about basic principles, we want to make an important observation, and that is when we talk about statistics, we often hear that individuals will research descriptively or inferentially. In other words, they will gather descriptive statistics or inferential ones. Now, you might say you've heard this comment before, but let's think about what that actually is. The question is really about what your goal is as a researcher. So the question is, are you trying to describe the sample of information that you have, or are you trying to infer to a greater population from the information that you've gathered? Now, let's think about this with an example. Let's say you gave a test to a class at a university, and you could get some basic descriptive information from that class. So you gave the test, and you might be able to determine some descriptive information like the mean, the median, the mode. You might also gather the range, the variance, and the standard deviation. And as you gather all of those pieces of information, you would have some information about the characteristics of that sample. Now, let's say that's all you were interested in. We would call that descriptive statistics, meaning we would say that you gathered that information in order to describe the sample that you are collecting the data from. Now, sometimes we actually don't stop there. Sometimes we like to make inferences to greater populations, and we're going to talk all about that idea. But basically, that idea is where I take a sample of something, so I might try to get a representative sample of a larger population and give a test to that group, and maybe infer that the rest of the population behaves in that same way. In that way, we call it inferential statistics. Now, let's go back and talk about descriptives one more time. When we talk about descriptives, we're saying we're describing, and then we talk about inferential, that's where we infer. Now, there is a very famous descriptive statistician out there. His name is Hans Rosling, and he does a great job in doing work in the area of world health. And so the first clip we're going to see today is from Hans Rosling, and it's his description of the health and wealth in 200 countries over 200 years. Let's take a look.
Visualization is right at the heart of my own work too. I teach global health. And I know having the data is not enough. I have to show it in ways people both enjoy and understand. Now, I'm going to try something I've never done before, animating the data in real space, with a bit of technical assistance from the crew.
So, here we go. First, an axis for health, life expectancy, from 25 years to 75 years. And down here, an axis for wealth, income per person, $400, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the differences between the countries of the world was wider than ever. United States was in the front, Japan was catching up. Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up with the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics. Most people today live in the middle, but there are huge differences at the same time between the best of countries and the worst of countries. And there are also huge inequalities within countries. These bubbles show country averages, but I can split them. Take China, I can split it into provinces. There goes Shanghai. It has the same wealth and health as Italy today. And there is the poor inland province Guizhou. It is like Pakistan. And if I split it further, the rural parts are like Ghana in Africa.
And yet, despite the enormous disparities today, we have seen 200 years of remarkable progress. That huge historical gap between the West and the rest is now closing. We have become an entirely new converging world. And I see a clear trend into the future. With aid, trade, green technology and peace, it's fully possible that everyone can make it to the healthy, wealthy corner.
Well, what you just seen in the last few minutes is a story of 200 countries shown over 200 years and beyond. It involved plotting of 120,000 numbers. Pretty neat, huh?
As you can see from his amazing models, Hans Rosling does a great job in using descriptive statistics to show us information from 200 countries around the world. Now, as we think about displaying data, of course, it brings up a very interesting question for us as researchers. And the question is, are you displaying the data in a meaningful way? Now, the next question to think about is, well, if I'm trying to display the data in a meaningful way, what would make sense in terms of my decision-making process? Well, of course, that brings us back to the data level of measurement. And as we've talked about in previous sessions, we identified the idea of categorical and continuous data as being two different types of data. One, categorical, being the categories of information, so that's nominal or ordinal data, and then we also identified continuous data as interval and ratio. So depending on the type of data you have, that really dictates some of the decision making that you would go into thinking about as you display your data. Now the next clip we're going to watch talks about different ways to display data. Let's take a look.
In this video, we will be talking about bar charts, pie charts, histograms, stem plots, and time plots. We can use these tools as a way of displaying data. We often use bar charts and pie charts to display categorical data, and we often use stem plots, time plots, and histograms for displaying quantitative data. Pie charts show the relative size of each value in relation to the whole. On the other hand, bar charts display the frequency on one axis and the values of the categorical variable on the other. You can think of bar charts as a way of tallying information. For quantitative data, we often use stem plots, histograms, and time plots to show information. We'll talk about histograms first. After collecting data from a population or sample, we can use a histogram to help us display the distribution of the data we collected. The frequency, or count, is displayed on one axis, and each count tells us how many data values fall within a predetermined interval on the other axis. This axis corresponds to the variable we have just measured. To read a histogram, you first pick one of the intervals and determine its height. So for the interval between 100 and 110, we see that the bar has a height of 8. This means that, from the data we collected, 8 people weigh between 100 and 110 pounds. For the next interval, we see that the bar has a height of 16. So this means that 16 out of the total people I collected data from weigh between 110 and 120 pounds. The rest of the histogram can be read in a similar fashion. A histogram is a form of a frequency distribution. Frequency distributions can be written in a table format, and they tell us how many data values fall within a certain interval. These intervals can be a little confusing. For example, if I recorded an individual's weight to be exactly 120 pounds, do I include them in this interval or this interval? By convention, we say that each interval does not include the right endpoint. So 120 is not included in this interval, and 130 is not included in the other interval. So in fact, 120 belongs to the second interval. Now you might be thinking, if the right interval isn't included, why don't I just rewrite my intervals like this? 110 to 119 and 120 to 129. Now the problem with this is that we don't have continuity. For example, if you weighed 119.7 pounds, there would be no interval that contains this value. Now a frequency distribution can be converted into something called a relative frequency distribution. The only difference between these two is that a regular frequency distribution shows a count, and a relative frequency distribution, as the name suggests, shows the relative frequency instead. It is called relative frequency because it represents the proportion of values in each interval in relation to the whole. To convert a frequency distribution into a relative frequency distribution, we will need to do some calculations. We start off by finding the total number of data values, and we do this by adding each frequency. We find that the total sum is equal to 50. Then, we will take each value and we will divide it by that sum. And as a result, we get the relative frequency values. To check if you have made the right conversions, you can add up all the proportions for each interval, and the sum should be equal to 1. The answer should be equal to 1 because we have used a ratio that relates our data to the total amount of data values. Because of this ratio, relative frequencies can be written in percentages. To convert to percentage form, all we do is multiply each value by 100%. In the same way, regular histograms can be converted into histograms that tell us the proportion of values for each interval. Now stem plots are like histograms, except they show each data point. Stem plots consist of stems and leaves. A leaf refers to the very last number, and a stem refers to all of the other numbers except the last number. Stems and leaves are usually separated by a line. For example, let's look at the number 117. The leaf is the last number, so this would be 7. The stem is all of the other numbers, so the stem is 11. On a stem plot, this would be written as so. Now let's look at the number 69. Using the same rules, we would get a leaf of 9 and a stem of 6. And on a stem plot, this would be written as so. Now when we have a string of leaves like this, it just means that I have the data points 30, 31, 32, 35, and 35. Notice how stem plots are constructed. Stems go down from low to high, and leaves extend outward from low to high. Depending on the dataset we are working with, sometimes we can get stem plots with too many leaves and we can get stem plots with too many stems. When this happens, we might not get a nice picture of the distribution, and as a result, we may not be able to get much information out of it. If we have a regular stem plot with too many leaves, we can convert it into something called a split stem plot. This conversion is called splitting the stems. To split the stems, we need to duplicate each stem. The first stem will run from 0 to 4, which corresponds to these values. And the second stem will run from 5 to 9, which corresponds to these values. The same logic can be applied to the rest of the stems. When we have too many stems, we can reduce the amount of stems by trimming the leaves. In this example, we have a very large dataset that goes from 201 all the way to 875. That's over 60 stems that we have to write. To trim the leaves, all we do is remove the very last digit. So notice for the number 201, the leaf is 1 and the stem is 20. After removing the very last digit, we get 20. So now the leaf becomes 0 and the stem is now 2. We would do the same process for each data value. By trimming the leaves, we get a better looking stem plot. Notice how we have reduced the amount of stems by doing this, and we have saved ourselves the trouble of having to write down over 60 stems. This is why trimming can be useful, but be careful when you read the stem plot after it has been trimmed. For example, for the top row, instead of reading it as 20, 20, 21, 22, 23, and so on, we read it as 200, 200, 210, 220, 230, and so on. This is because the original data was in the hundreds place. Now the last type of stem plot we will be looking at is called a back-to-back stem plot. Back-to-back stem plots are used to display and compare two distributions by using the same set of stems. So for example, we could compare data from males and females, or data from cats and dogs. Another way to display quantitative data is by using a time plot. Time plots show how a variable changes over time. By convention, time is always plotted on the x-axis, and the values of a variable are always plotted on the y-axis.
So in that clip, we were able to see various ways that data are displayed. Of course, one of the areas that was talked about was histograms. And when we think about histograms, this is something that we see pretty commonly in statistics. This idea that we would graphically display the data in that particular way. Now, as you're viewing this show, you may come to this show with some basic knowledge about statistics. Others of you maybe not have a background of statistics. And so as we think about that, we want to stop and observe a few different key areas of central tendency and 3 key areas of dispersion that we want to identify and think about as some basic foundation when we think about histograms. So let's talk about the idea of central tendency. When we talk about central tendency, we have 3 really familiar statistics that we talk about, and that's mean, median, and mode. So we identify the mean as the average score, we identify the mode as the most frequently reported score, and we identify the median as the middle score. So when we think about those 3 statistics, we think about what they tell us about how the gathers centrally, or central tendency. So let's take an example of test scores and think about how we could get an average test score, and then we could also get a median, which is a middle test score, and then we could also get a mode, which is a most frequently reported score. And as a teacher, when I see tests come back, I look at all of those statistics to understand how the data are gathered together. Now, another concept to talk about is this idea of dispersion or spread. The notion that there are 3 really central statistics that we talk about in terms of how the data are spread out. So the first one is range, the second one is variance, and the third is standard deviation. Now when we think about those 3 areas, we think about range being the idea of the range of the data. So that's the highest data point, subtract the lowest data point to get the range. And then we'd also think of variance, and that is how spread out the data are. Now, when you think about the histogram that we saw, this is the notion that the data are very spread out, meaning there's a wide variance of the data versus low variance, where we'd say maybe the data would be closely gathered, maybe only 2 or 3 bars in the histogram. And then we'd also see that the bumps of the histogram would be driven up. That's something we call kurtosis. So when we think about variance, that's really simply, are the scores varied or are they not? Now, when we think about standard deviation, we know that this is related to variance. The only difference is it's in standard measurement. So what does that mean? It's how much we expect the data to deviate from the mean in standard units. So in other words, variance and standard deviation are very similar indicators, but one is in standard units and one is not. So let's take a look at the standard deviation more closely and take a look at this clip in order to understand it.
Have we discovered a new particle in physics? Is a manufacturing process out of control? What percentage of men are taller than LeBron James? How about taller than Yao Ming? All of these questions can be answered using the concept of standard deviation. For any set of data, the mean and standard deviation can be calculated. For example, 5 people may have the following amounts of money in their wallets: $21, $50, $62, $85, and $90. The mean is $61.60, and the standard deviation is $28.01. How much does the data vary from the average? Standard deviation is a measure of spread, that is, how spread out a set of data is. A low standard deviation tells us that the data is closely clustered around the mean, or average, while a high standard deviation indicates that the data is dispersed over a wider range of values. Standard deviation is used when the distribution of data is approximately normal, resembling a bell curve. Standard deviation is commonly used to understand whether a specific data point is standard and expected, or unusual and unexpected. Standard deviation is represented by the lowercase Greek letter sigma. A data point's distance from the mean can be measured by the number of standard deviations that it is above or below the mean. A data point that is beyond a certain number of standard deviations from the mean represents an outcome that is significantly above or below the average. This can be used to determine whether a result is statistically significant or part of expected variation, such as whether a bottle with an extra ounce of soda is to be expected or warrants further investigation into the production line. The 68-95-99.7 rule tells us that about 68% of the data fall within one standard deviation of the mean. About 95% of data fall within two standard deviations of the mean, and about 99.7% of data fall within 3 standard deviations of the mean. The average height of an American adult male is 5'10", with a standard deviation of 3 inches. Using the 68-95-99.7 rule, this means that 68% of American men are 5'10", plus or minus 3 inches. 95% of American men are 5'10", plus or minus 6 inches, and 99.7% of American men are 5'10", plus or minus 9 inches. So, this means only about 0.3% of American men deviate more than 9 inches from the average, with 0.15% taller than 6'7", and 0.15% shorter than 5'1". This reasoning suggests that LeBron James is 1 in 2,500 and Yao Ming is 1 in 450 million. In particle physics, scientists have what are called 5 sigma results that are 5 standard deviations above or below the mean. A result that varies this much can signify a discovery, as it has only a 1 in 3.5 million chance that it is due to random fluctuation. In summary, standard deviation is a measure of spread. Along with the mean, the standard deviation allows us to determine whether a value is statistically significant or part of expected variation. Thanks for watching. See you next time.
As we can see in the clip, we understand the idea that the standard deviation is the tool that helps us understand if something is significantly different. Now, as we talk about that, of course, we have to observe a few different things that are related to the material and statistics that we've covered so far in our class. Now, you may remember doing the SPSS project that we did for the first homework. And in that SPSS project, we ran basic frequency data. So the first question you might be asking is, how do we calculate the mean and the median and the standard deviation? And the answer is, for our purposes, we have the computer do it for us. So when we think about those pieces of statistics, we know that we ran the frequency data and it gave us an average age of our class. And that average age was 39.35. So we know that that was the average that we got. And we also knew that the standard deviation on that printout was 10.89. Meaning that the average age in our class is 39.35 and the standard deviation 10.89. So if we rounded those numbers, it would probably be easier to talk about. Let's think about the average age being 39 if we round it down, and then the standard deviation if we round it slightly up being 11. Now, what does that mean? That means that when we think about the concept we just saw on the video, we understand that with that average age, if we went down 1 standard deviation, we would subtract 11. And if we went up a standard deviation, we would add 11. And that would mean that 68% of our class falls between 28 and 50 years old. And that's just representative of the matrix that we analyzed. And if we went 1 more standard deviation down, and 1 more standard deviation up, we would understand 95% of what we expect to be the age range in our class. And that means that we have the numbers 17 to 61. in terms of our range for 95% of the class. Now you might say, I don't get why this really matters. Well, if someone were to walk into class and they were, say, 65 or 70 or 75, and they announced to us that they were significantly older, we would say, yes, older than the measurement that we've done, but to be significantly older, they'd have to be outside of those standard deviation parameters. Now, the next question you might be asking yourself is, where do those parameters come from? Like, where do those basic stats get their calculations from? And the good news is that some experts in statistics have figured that out for us. And that's based in a bigger conversation where we start to talk about the normal distribution. So as we think about that concept, let's take a look at this clip that describes the normal distribution.
All right, I want to show you what a normal distribution is all about in statistics. And there are three things that should come to mind when you read the words normal distribution. The first thing is that you have what's called a bell-shaped curve that basically looks like this right here. It's bell-shaped curve, okay? That means that the mean, which is kind of sitting right here in the middle, has the most data that's sitting around it on either side of the mean. I'll talk a little bit more about that later. But definitely, bell-shaped curve is one of the first things that should come to mind when you read that word normal. The second thing that should come to mind when you hear normal distribution is that the total area under the curve is equal to 1. So all of this area underneath this bell-shaped curve, all of it, including everything out here in the tails as they get smaller and smaller, is a total area of 1. And there's one more thing. The third thing that should come to mind is that this bell-shaped picture here is symmetrical, right? It's symmetrical. And that comes into play and is very handy. It's kind of a geometric term for later problems. So if I was to kind of split this thing right down the center here, you would see that half of this picture over here, if the whole thing is 1, is 0.5, and the other half is 0.5, giving you a total area, everything from here all the way over to here, right? Total area all together, everything under the curve here, that gives you a total area of 1. So those three things should come to mind when you hear the words normal distribution. It's bell-shaped, total area is 1, and it's symmetrical. Let me just go one more step and show you what I mean by, and perhaps you've seen this as well, not only are we talking about now a normal distribution, but something called a standard normal distribution. So a normal distribution, again, are these three things, right? Bell-shaped, total area is 1, and symmetrical. Standard normal kind of uses these three things, but kicked up one more notch, and two other things, we'll mark them 4 and 5, how's that? Two other things should come to mind when that word standard is used, right? Two other things should come to mind. Number one is that the mean, and that Greek letter is mu, which stands for population mean, or population average, same thing, that the mean is going to be a 0. All right, that's what standard means. Standard means that the mean, population mean, is 0. And the other thing that it means is that this Greek symbol sigma, which is lowercase sigma, and that means population standard deviation, is automatically 1. So these two things are also part of what the standard normal distribution is, right? So there's normal distribution, which means these three things. We covered those a second ago. But when you read the word standard normal, these two things also come into play, which means, going back to this picture here, that the mean sits right here in the middle, is 0. The average is going to be 0. And that one standard deviation, right, one standard deviation in either direction is also into play. So that's what we mean, and there's this other idea called the empirical rule, but we can get into that another time. If, 68% of your data is sitting smack within one standard deviation. But this is just a real rudimentary level of what we mean by a standard normal. Means that the population mean is 0, population standard deviation is 1, and when we say normal, we mean it's bell-shaped, total area is 1, and it's symmetrical. Hope that helps.
As you can see, that's a great discussion of the normal distribution, and then also the idea of standardizing the normal distribution and giving us the tools to judge significance. Now, it's possible that you have a background in stats, or maybe you had high school stats. And when you have basic stats, a lot of times they use a traditional method for evaluating significance. And this involves comparing the calculated value that you obtain, maybe through your hand calculation, to something called a critical value. And that is like the old-fashioned way of determining significance, where we look up on a chart and see if our numbers equal to or greater than the critical value in order to determine significance. Now, we're not going to actually use that method. In this class, we're actually going to, because we have computers, because we have help in making these calculations, we are going to use what is called the p-value method. And what does that mean? That means that we are going to understand the way to determine significance by looking at the p-value. And as we do that, we can run SPSS programs, we can run all kinds of different other data programs and get a p-value and then know instantly whether we have a significant result or not. So let's take a look at this next video, and it will give us a little more information about the p-value method.
All right, in this video, I want to show you the basics of hypothesis testing for the non-traditional method, or the p-value method to be more specific, all right? The p-value method. I have shown in a separate video the basics of hypothesis testing using the traditional method. So there are two different kinds. Actually, probably more than two, but I'm only showing you two in my videos. So real quickly here, the basics of hypothesis testing, no matter what method you're using, traditional or p-value, is that there are going to be two types of hypotheses, right? There's the null hypothesis and there's the alternative hypothesis. Let's see, almost every book I've used uses H sub 0 or H naught as the null hypothesis, and no matter what parameter you're talking about, whether it's a proportion or a mean or a standard deviation, the null hypothesis always uses an equal sign, right? It always has an equal sign in it. The alternative hypothesis, maybe your book uses H sub 1 or H sub A, whatever the case may be, always uses a symbol that is not an equal sign, right? So in this case, it's a less than symbol or a greater than symbol or a not equal to symbol. But no matter what type of hypothesis testing it is, you will always be given some level of significance here, okay? So whether it's 0.01 or 0.05 or 0.10, something like that. Now that level of significance is called alpha, right? It's called alpha, which is the Greek lowercase letter A here. That's the first letter of the Greek alphabet. So and we're not restricted to 0.01, 0.5, or 10% or something like that. It could be any other type of level of significance, but these are the three more popular ones. Okay, the other thing I want to tell you about, and keep your eye on these three alternative hypotheses here, right? So less than, greater than, or not equal to, is depending on what kind of a test we're talking about, you might have a left tail test, a right tail test, or a two tail test. And that all depends on the alternative hypothesis. So, right, so I'm using H sub 1 as my alternative hypothesis notation here. But if the alternative hypothesis is less than, we have a left tail test. If it's greater than, we have a right tail test. Or if it's not equal to, we have a two tail test. We have a two tail test. So that is also important and significant here. And what do I mean by that? I didn't show this in my previous video, but for example here, let's say I got a little package here of push pins. Can you guys see that? I think you can see that in the video here now. All right, and it says that there should be 100 push pins in here. Now, if I think I got gypped, right, and I'm thinking they're putting less than 100 push pins in there, then less than would be a left tail test. All right, or maybe I'm thinking they're being generous as I buy these push pins, and they're actually putting more than 100 in. Well, more than would be a right tail test, greater than. Okay, where if I state the claim, right, all of these are claims here. If I state the claim as, I don't think they're putting 100 in there, Right, notice I'm not specifying when I say I don't think they're putting 100 in there. I believe there aren't 100 in there. I'm not specifying whether it's less than 100 or greater than 100. So in that case, it would be a two-tailed test. So depending on the wording that you see, it could be one of those types of alternative hypotheses or claims. Okay. So what I showed again in a previous video, you can look it up, is the traditional method. And what I'm going to show you in this video is the p-value method, right? But notice I wrote on this little piece of paper here that both methods, doesn't matter which method you're using, both methods require you to find a test statistic. So both methods use a test statistic. Whether your test statistic is with proportions, that would be p hat minus p over the square root of little p times q over n, or maybe you're dealing with sample means and population means, and so your test statistic would be with this formula here. So you probably are familiar with those formulas, okay? But regardless of the method, both of them use test statistics, okay? So what the p-value does, separately from the traditional method, is this, right? The traditional method uses something called critical values. Right, I'll just put this on here real quick. The traditional method uses something called critical values. Well, guess what? And I'm going to cross that out. The p-value method does not use that at all. All right, p-value method says, look, I don't really care about the critical value whatsoever. So that's kind of a nice little thing here. So let's say that, for example, we were dealing with a right tail test. Right, so I'll draw a little right tail here. Right. So let's say, for example, we were dealing with a right tail test. That's our h sub 1 is a greater than. Then what the p-value says is this. All right, what the p-value says is this. What we're going to do is we're going to find, using the formulas that I just showed you a second ago, we're going to find, put here find, we're going to find our test statistic. All right, we're going to find our test statistic using that formula you just saw on the previous page. And then we're going to put that in. I'm going to write this as how about TS, all right, test statistic. We're gonna put that in here, and this is a right tail test. Let's say our test statistic here, I don't know, I'm just kind of making something up, but let's say our test statistic came out to be something like how about negative 2.61, for example, all right? Or sorry, positive. This is on the right hand side. So let's say our test statistic came out to 2.61. Okay, so for example here, 2.61. Now, do you see that this area, the area sitting over here to the far right of this, is 0.0045. Okay, you can look that up. This area is 0.0045, right? It's 0.0045, and you can look that up on a table if you want to, or you can use Excel to figure that area out. But here's the deal. That area is what's called our p-value. All right, so this area is the p-value now. All right, so the area sitting over here to the right, in this case of a test statistic, is our p-value. Okay, so that area, in this case 0.0045, is our p-value that we are going to compare. All right, we're going to compare the p-value to our alpha, to our level of significance, and that's how p-value method, the testing, works. So in our case, I have a p-value of 0.0045, and let's say that we had an alpha. Let's say that we were looking for a level of significance of 0.01, for example. I don't know, we'll pick on 0.01. All right, so our alpha, our p-value is sitting right here. Our alpha is sitting right here of 0.01. And as you compare these two, do you notice that this one here, our p-value, is less than 0.01? All right, and there's a phrase that goes along with this. If the p-value is low, right, lower than my alpha, my level of significance, then the null must go. So we're going to take the null hypothesis and we're going to reject it. Right, we're going to reject it. What if, though, let's just say, for instance, what if our p-value was greater than our alpha? All right, I know this is not the case in this particular case, but let's say we had a p-value of 0.028 something like that, right? And in this particular case, look, our p-value rather, would be bigger than our alpha of 0.01. So if this is the case, if your p-value is high, right, is larger than your alpha, then the null must fly. So we're going to keep, right, the null hypothesis. So hypothesis testing is all about the null. We either reject it or we, in my case, I put keep here, but technically the term is we fail to reject. Okay, so this is a reject here if the p-value is low, and if the p-value is high, then the null must fly. What we're really doing is we are really failing to reject. That's what's going on here when I say the word keep. Okay, we're failing to reject. So if the p-value is low, the null must go. If the p-value is high, the null flies. And what that really means is, if we reject the null hypothesis, what we're in essence saying is we support the claim of the alternative hypothesis, right? If we keep the null hypothesis, what we're in essence saying is this may be true, therefore we don't have enough evidence to support our claim. Right, so the wording of this is pretty tricky. You've got to get your mind around that as well. But this is how p-value testing works.
Now, as we can see, this is a great introductory idea to talk about the null hypothesis and the alternative hypothesis. Now, I want to back up a little bit here and talk about the academic journals that you may have been reading. So when you read an academic journal, you know that there's the review of literature, and then it leads up in a quantitative study, it leads up to the hypothesis. And you see there either a one or two-tailed hypothesis, and we've gone over that in a previous session. So you see the alternative hypothesis, either one or two-tailed, or maybe you see a group of hypotheses. Now the comment to tell you is that those are being compared to the null hypothesis. What does this mean? Well, we assume that there's nothing special happening in this research. So that's our assumption going in statistically, that there's nothing going on, nothing special is happening. And so when we ask these questions, one-tailed is something significantly higher or is significantly lower, or maybe we say significantly different in the case of the two-tailed hypothesis, we are suggesting that there's something special happening. And then that tells us which one to adopt. So you saw in the previous video that the idea of keeping the null means that we didn't find enough evidence. In other words, we failed to reject the null or the notion that nothing's happening. But if we find that we have very special results, very significant results, then we would be able to adopt the alternative hypothesis. In other words, reject the null and then rule in favor of the hypothesis that you see in the journal article. The thing that's interesting is to understand what's behind it so that you understand the role that the null plays in this conversation. Now, of course, we could talk about p-values here. And when we think about reading like an output file in SPSS, we know that as we read that file, we know that it'll generate a p-value for us. And so all that video was basically showing us is what to do with the p-value. And what we do is we compare it to the alpha level, which is the established significance parameter that we decided as a researcher. Now, it's very common for that number to be 0.05 in social science research. I'm sure you've seen that many places, or perhaps 0.01 is a number we might see very often. So when you read the journal article, you sometimes see like 0.03, or you see less than 0.05, or you see 0.001. And all of that is to show the reader how special those results are. And so what do we do on the most basic level? We figure out the p-value in order to know what we can say is a special result versus not, and we have the computer do it for us. Now, as we saw in this video, he had the phrase that if the p-value is low, then the null must go, meaning the lower that p-value, the more special that result is. And on the other side, then we would say if the p-value is high, then the null must fly. And that means that the opposite is true. So that's just basically some ideas around the null hypothesis and this idea that we can use the p-value to determine significance. So if you've been someone who's learned the traditional method and you've examined critical values in the past or compared statistics like calculated values, just know that how we're going to do it is to take all of that information generated in our technological age and evaluate the p-level and determine significance that way. Now, our next topic is to talk about experimental design. And as we talk about experimental design, of course, we're going to kind of turn our conversation into kind of a different direction, really. And this is where we do our research involving experiments. And when we talk about experimental design, we're talking about this notion that we design it specifically in order to assign causation. Now, of course, we can't prove it entirely, but we can control a lot of factors about the experiment in order to try to assign causality. So let's think about a couple of parameters that are important, or terms that you might hear. The first one is that sometimes we hear that we're running a true experimental design versus a quasi-experimental design. And when we think about true versus quasi, what do they mean by this? Well, what they're talking about is how the participants were selected. So what does that mean? That means that in a true experimental design, all of the people involved in the study had an equal chance of being selected to any of the conditions in the study. In other words, they had an equal chance of being in any group. But when we have a quasi-experimental design, it means that we didn't use random selection for participants. It means that we actually kind of fixed who was in what group, or we didn't have the means to be able to make that randomization happen. Now, you might say, well, why does the random selection matter? And when we talk about people being equally or have the equal chance of being selected in a research study, then we can do things like infer, a concept we talked about earlier. And so that randomization actually is a very important distinction between the idea of true and quasi-experimental design. Now, of course, there's different reasons, and we can read about those reasons why we might use true or quasi-experimental design, but we know that the real designs that are out there that are true actually give us the best data in order to do this job of assigning causality. Now, let's talk about a couple of basic concepts in experimental design. As we talk about it, of course, we have to talk about the idea of control, because controlling in an experiment is very important. We could also talk about the idea of a treatment, and that's where we give a treatment to maybe one group and not to another. So we might have the control group not get that treatment, but we might have the treatment group get it. And so we identify that being a key term. Of course, we also want to talk about placebo effects, because that relates to this idea of not getting a treatment. And then finally, we want to introduce the concept of the double blind, and that's the idea that not everybody has a visual understanding or notion about how the research is conducted in order to try to control the effects that might show up in the outcomes of the data. So this next clip gives us a little more insight about those introductory concepts.
In this video, we will be talking about the placebo effect, control groups, and the double-blind experiment. A placebo is known as a fake treatment. It could be known as a fake pill, drink, lotions, or any type of treatment that is known to have no medical effect. However, a placebo may have psychological effects. These psychological effects are known as the placebo effect. By believing and expecting something to work, it will work. For example, if you believe that a pill will make you feel better, then it will make you feel better, even if the pill is fake. In other words, the pill is a placebo. If you think that the same placebo will make you feel sad, then it will make you feel sad. This is the placebo effect. Placebos can be used for a control group. The control group receives the placebo as a treatment. In other words, the control group receives a fake treatment. Now, why would you want a control group? A control group gives you something to compare your results with. So suppose an unknown company were giving pills to people at the gym to help them gain strength. After 1 month of treatment, 75% of the people taking the pills report that their strength has increased. Does this mean that the pill was the cause? No. So far, this is an observational study. We cannot say for sure. Maybe there are lurking variables that are present, like diet and the type of workout routine. Some people may have better diets or workout routines, which may have allowed them to become significantly stronger than everyone else. This is why we need a control group. We could randomly assign participants into 2 groups. One group will be the control group, and the other group will be the experimental group. Each group will have to get the same thing. So each group will receive the same diet, each group will have the same workout routine, and each group will get the same amount of sleep, and etc. The only thing that is different between these two groups is that the experimental group receives a pill and the control group receives a placebo. A good placebo should look and taste like the actual pill. If the percentage of people in the experimental group significantly gain more strength than the people in the control group, then we can say that the pill is actually the cause for gaining strength. You can think of the control group as just doing nothing to it. We have the placebo for humans because we can perceive things psychologically. If instead our experimental units were plants, which lack a nervous system and the ability to perceive things psychologically, then we don't really need a placebo. So the experimental group of plants receives the treatment and the control group gets absolutely nothing. And then we would compare the results from the experimental group and the control group. Going back to our first example, if the control group knows that they are receiving the placebo, then this will obviously eliminate the placebo effect and it may skew the results. We need an equal playing field, where neither group knows if they got the placebo or if they got the actual treatment. To prevent bias and the manipulation of results, the experimenter should also not know which group is which. This setup is called the double-blind experiment, where the experimenter and the subjects do not know which of the groups being studied is the experimental group and which of the groups is the control group. The double-blind experiment is good for eliminating biased research results.
So we can see those are some introductory ways to try to control the elements of an experiment. Now, when we think about that, that's how I want you to think about experimental design. It's the idea that through our design, we can carefully examine and control different aspects of the experiment. Now, in that video, they talked about the placebo effect. And of course, that directly relates to the type of research we care about because we know we have humans in our studies. So when we think about that, that's probably the next conversation we need to have. This idea that the placebo effect brings about some of the psychological effects that are unique to humans. And you saw the comparison between the plants and the human consumption of the pill. So let's take a look at this next clip that explores the placebo effect specifically.
In 1996, 56 volunteers took part in a study to test a new painkiller called Trivaricane. On each subject, one index finger was covered in the new painkiller, while the other remained untouched. Then, both were squeezed in painful clamps. The subjects reported that the treated finger hurt less than the untreated one. This shouldn't be surprising, except Trivaricane wasn't actually a painkiller, just a fake concoction with no pain-easing properties at all. What made the students so sure this dummy drug had worked? The answer lies in the placebo effect, an unexplained phenomenon wherein drugs, treatments, and therapies that aren't supposed to have an effect and are often fake miraculously make people feel better. Doctors have used the term placebo since the 1700s, when they realized the power of fake drugs to improve people's symptoms. These were administered when proper drugs weren't available, or if someone imagined they were ill. In fact, the word placebo means "I shall please" in Latin, hinting at a history of placating troubled patients. Placebos had to mimic the real treatments in order to be convincing, so they took the form of sugar pills, water-filled injections, and even sham surgeries. Soon, doctors realized that duping people in this way had another use: in clinical trials. By the 1950s, researchers were using placebos as a standard tool to test new treatments. To evaluate a new drug, for instance, half the patients in a trial might receive the real pill. The other half would get a placebo that looked the same. Since patients wouldn't know whether they'd received the real thing or a dud, the results wouldn't be biased, researchers believed. Then, if the new drug showed a significant benefit compared to the placebo, it was proved effective. Nowadays, it's less common to use placebos this way because of ethical concerns. If it's possible to compare a new drug against an older version or another existing drug, that's preferable to simply giving someone no treatment at all, especially if they have a serious ailment. In these cases, placebos are often used as a control to fine-tune the trial so that the effects of the new versus the old or alternative drug can be precisely compared. But of course, we know the placebos exert their own influence too. Thanks to the placebo effect, patients have experienced relief from a range of ailments, including heart problems, asthma, and severe pain, even though all they'd received was a fake drug or sham surgery. We're still trying to understand how. Some believe that instead of being real, the placebo effect is merely confused with other factors, like patients trying to please doctors by falsely reporting improvements. On the other hand, researchers think that if a person believes a fake treatment is real, their expectations of recovery actually do trigger physiological factors that improve their symptoms. Placebos seem to be capable of causing measurable change in blood pressure, heart rate, and the release of pain-reducing chemicals like endorphins. That explains why subjects in pain studies often say placebos ease their discomfort. Placebos may even reduce levels of stress hormones like adrenaline, which can slow the harmful effects of an ailment. So shouldn't we celebrate the placebo's bizarre benefits? Not necessarily. If somebody believes a fake treatment has cured them, they may miss out on drugs or therapies that are proven to work. Plus, the positive effects may fade over time, and often do. Placebos also cloud clinical results, making scientists even more motivated to discover how they wield such power over us. Despite everything we know about the human body, there are still some strange and enduring mysteries, like the placebo effect. So what other undiscovered marvels might we contain? It's easy to investigate the world around us and forget that one of its most fascinating subjects lies right behind our eyes.
As we can see, the fact that we're measuring humans, of course, is a complicated process. Now, that notion of the placebo effect, you heard some of the dangers of using that in experimental design. Of course, one we would highlight is the idea that if your patients or your participants would have a highly negative effect, like not getting medicine for a disease they are known to have, then we would of course know that giving them a placebo would be a very dangerous practice, in fact, unethical indeed. So when we think about the placebo, of course we want to understand that behind that idea is this idea of control and comparison. And then we'd also know that we have some other options actually in terms of experimental design to try to handle that matter. So let's take a look at a couple of very strategic designs that are used in experimental design that will help us see some examples of where we might provide those controls. And we're going to talk about randomized design, we're going to talk about randomized block design, and then we'll also talk about matched pair design. Let's take a look at this clip that goes through each of those.
In this video, we will be looking at experimental designs. The types of experimental designs include the completely randomized design, the randomized block design, and the matched pairs design. In a completely randomized design, each experimental unit is randomly assigned to a random group to receive a different treatment. Each unit in the same group will receive the same treatment, and at the end of the experiment, you will compare the results from each treatment. Show how a completely randomized design would be used in the following example. A researcher wants to conduct an experiment to determine which environment is best suited for studying: a library, in one's own room, or outside. A total of 30 university students volunteer to participate in the experiment. So we have 3 treatments: the library, in one's own room, and outside. Since we have 3 treatments, we will have 3 groups receiving the treatments. Since there are 30 university students, these 30 subjects will be randomly assigned into 3 groups to receive the treatments. Since there are 30 people, each group will have 10 people, and at the end of the experiment, we would compare the results from each treatment. Let's say that the researcher believes that gender has an effect on the results. In a case like this, we would use a randomized block design. A randomized block design doesn't immediately randomly assign experimental units to receive treatments. We first assign people into a block based on a characteristic that is expected to influence their response to the treatments. In this example, gender would be the blocking variable. So first, we separate our experimental units based on gender. One block will be for females and one block will be for males. There are 18 females and 12 males. Then, the experimental units in each block will be randomly assigned to 3 different groups to receive a treatment. So let's make a diagram out of this. We are looking at a randomized block design, and gender was the blocking variable. We started off with 30 university students, and we separated these students into two blocks. One was for males and one was for females. We determined that there were 18 females and 12 males. We will have the females be randomly assigned to 3 different groups, and each group will have 6 females, and each group will receive different treatments. For the males, we are doing the same thing, except we have 12 males, so we will randomly assign 4 males into each group. And at the end of the experiment, we will compare the results within each block. The last type of experiment we'll talk about is the matched pairs design. In a matched pairs design, we are only comparing 2 treatments by using the same or similar experimental units. If we are using the same experimental units, we could have an example like this. What type of gasoline is more efficient? Type A gasoline or type B gasoline? 3 cars will be used in this experiment. Describe how a matched pairs design would be used. If we are using the same experimental units, then each experimental unit will receive both treatments. So we have 3 cars, and each car will receive the 2 treatments, one with type A gasoline and one with type B gasoline. We would use the same car for each treatment, and which treatment goes first will be random. So for example, we could drive with type B gasoline first, then once all the gasoline is finished, we would fill up the car with type A gasoline using the same quantity, and at the end of the experiment, we would compare the efficiency of the gasoline. There are cases when we can't use the same experimental units for a matched pairs design, and we would have to use similar experimental units. For example, a researcher is trying to determine whether or not sleep deprivation has an effect on test scores. Describe how a matched pairs design would be used. Well, we could try giving both treatments to the same experimental units like we did in the other example. In other words, we could have the same person write the test on 2 different days, one being sleep deprived and the other with sufficient sleep. The problem with this is that we can't have the same subject write the same test because they would know what's on the exam when they write it the second time, so that would be kind of unfair. Instead, we could start off by pairing up students with similar GPAs. So for example, the 2 students with the highest GPAs would be matched up together, and the 2 students with the lowest GPAs would be matched up together. Then, each pair will be split up and randomly assigned to one of the 2 treatments. So for a pair, one person will get the sleep-deprived treatment, and the other person will get a normal amount of sleep. Then, we would compare the results for each pair, and we will also compare all of the results. So for example, if we saw that the sleep-deprived people were consistently getting lower test scores than the people who got a regular amount of sleep, then we can say that sleep deprivation was actually the cause for a bad test score. So let's quickly recap. These are the experimental designs we talked about. In a completely randomized design, each experimental unit is randomly assigned to a random group to receive a different treatment. This is what the diagram would look like. Group N, or treatment N, means you can have any number of groups or treatments. A randomized block design first assigns people into a block based on a characteristic that is expected to influence the response of the experimental units to the treatments. Then, a completely randomized design is performed within each block. This is what the diagram would look like. Block N means that you can have any number of blocks that you want. For a matched pairs design, we saw 2 scenarios, one that uses the same experimental units and one that uses similar experimental units. Both of these involve the comparison of only 2 treatments. If you are using the same experimental units, each experimental unit gets both treatments. This is what the simplified diagram would look like. If you are using similar experimental units, we first pair up similar experimental units, then each pair is split up and randomly assigned to one of 2 treatments. This is what the simplified diagram would look like.
As we can see, experimental design can be very complicated. So one question you might be asking yourself is, do I have to memorize and know all of these experimental designs? And the answer is, of course not. For most of our research today, we actually have a lot of manuals that help us understand the designs. And so really what we want to get from this data, or from this video and from our reading, is this notion that we use experimental design to control certain outcomes from being part or interfering with the data. And we use experimental design to be able to evaluate and make fair comparisons. Now, of course, another thing we'd observe about experimental design is it's very highly probable that when you use experimental design, you are looking for differences. You saw throughout the video the word compare. When we think about the idea of comparing, we talk about looking for differences in terms of the experimental design outcomes. And so we might see different performance or averages or whatever it is that we're measuring. And so we know that this is really often used in the context of difference testing. But we also know that it's necessary to control many elements of the experimental design because we are involving humans, and we know there's so many factors that can be related. Now, one experimental design we haven't talked about is this idea of pre-test and post-test. And so what happens really is there's two groups going on, and we say that this top group gets a pre-test, and then they might get a treatment, and then a post-test. Whereas the other group might get a pre-test, but no condition or treatment, and then they will do a post-test. The easiest way to think about this, I think about, is the idea of an inhaler. So you might take an actual breathing rate for your pretest in a set of participants that are assigned to that condition, and then you might give them an inhaler, and then you might again assess their breathing. I know many times that's done with a device called the pulse oximeter. You may have seen this in the hospital, where someone shines a light through someone's finger in order to detect the oxygenation level of the blood. So that might be our pretest, to do the pulse oximeter on that person's finger, and then give them an inhaler, and then do the pulse oximeter again. Now on the bottom level, we would have our control group, and that's where we might do the pulse oximeter and measure the level of oxygenation of the blood, and then we would give them an inhaler, but it wouldn't have anything in it. So you can think about that related to both videos, right? The idea that I would give a placebo, I would give a treatment that isn't really a treatment. It has nothing in it. And then I would also do the post-test, which is that pulse oximeter again. You can see that's kind of a very classic experimental design, and it's designed to compare to see, is there a difference when we give an inhaler to one group that actually has medicine in it versus an inhaler that has no medicine in it. Now, of course, that would be dangerous if we were in a life-threatening situation, so of course we'd never do it in that context. But you get the idea. That's the idea that I can give a treatment to one group and not to another group in order to look for difference testing. Well, that kind of wraps up our content for today. Today we've talked about the idea of some basic statistical principles, and then we also visited the concept of experimental design. And as we looked at that, we saw that there's many aspects that we can do to control the experiment and to administer treatments, and that there's many designs out there for us to examine. Well, thanks for joining me today on the show. And this is Dr. Pamela Kreiser, hoping that your day is not just different, but significantly different.